तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we discussed the various p-type and n-type dopants with reference to gallium arsenide. We also said that in the case of indium phosphide also almost the same dopants hold good. After all, it is 3,5 in general, not gallium arsenide, not indium phosphide or gallium nitride. Now, we will go further on to some of the other impurities which are present, either present or you deliberately introduce to modify to suit to your requirement. We will see today, we will start seeing or discussing a brief overview of gallium arsenide technology for high speed devices. Okay. Now, when you see this gallium arsenide technology, what we would like to see is first some aspects of semi insulating, that is Si within the bracket, semi insulating gallium arsenide substrate. In fact, that will be the starting substrate. Why should we have that, etc., we will see soon. Okay. Now, on the top of that substrate, you will have a epitaxial active layer. In fact, okay, this is the epitaxial active layer of gallium arsenide on semi insulating substrate. On that we will make the devices. So, what we are taking a look at is these three aspects one by one. This itself will take us some time, then we will go into this most probably in my next lecture on these. There onwards, we will not look back into materials, we will look into devices. Just watch the slide. So, what happens? I will go back if you have missed it. Semi insulating substrate starting, on the top of that you see the layer grows, that layer is epitaxial layer. So, starting substrate, once more the starting substrate is the semi insulating gallium arsenide substrate, and on the top of that you will have epitaxial layer which will be the active layer. Now, before we go any further, what we have to see is, I will just go to the board and explain some of these things. Why do we need this semi insulating substrate, or why do we need an insulator at all? Can't we have the entire layer as the active layer? For example, I want to make a n channel MOSFET. What do? We take a p-type substrate, okay, grow n channel devices. That is what we do. Can't we do similar thing? Okay. Now, notice when you have a semiconductor material like this, whether it is n type or p type semiconductor, ultimately you do not use the full wafer. What is active is only a top layer, that is active layer. Okay? That is the active layer. Whether you talk of MOSFET, JFET, bipolar transistor, the active layer is very thin. Rest of this layer, what does it do? It provides only the mechanical support. Now, in the process of providing mechanical support to that active layer, it does lot of harmful things. The harmful things that it does are some of the capacitances which come from the device to the substrate, and also the capacitance when you interconnect the devices, the capacitance of the interconnection layer, or routing capacitance or routing capacitance, whatever you want to call it, a capacitance when you interconnect, that capacitance with respect to substrate, that also comes up here. Okay. So, that is why when you want to go to high speed, you want to cut down all capacitances. We have seen it right at the beginning. How to cut down the capacitance? Replace this particular layer, entire bottom layer, by means of an insulating layer. An insulating layer, so that the junctions, capacitance, etc., can be reduced. We will see how it happens. Okay. And also, when you have a thick insulating layer, when you have a interconnecting wire going through one device to other device, the capacitance of the layer with respect to substrate, okay, that is the capacitance, because capacitance of this layer, okay, that can be reduced, because it can be made thick. For example, with respect to that, up to this point, if you have, I remove this layer, let us say when interconnecting layer, I can remove this layer. So, the interconnection goes through this like this, that is the capacitance. Thick layer, capacitance is very small. So, this is one of the key things in high speed devices and high speed circuits made out of high speed devices. This is why people are looking more and more into substrates which are insulating. In the case of MOSFET, way back 20 years back, people have spent their energy on like this silicon, on sapphire, silicon on sapphire, for example. Okay. I think double P. Sapphire is Al2O3, it is an insulator, very costly material. But still, if you want high speed, what they have done in silicon technology for high speed, because it is not as if the high speed is proprietary of the compound semiconductors. In silicon itself, people have been trying, it is like this. Sapphire. On that you grow silicon. This is insulator. This entire thing is an insulator. Because it is Al2O3, it is an oxide. In fact, for defense applications, when high speeds are required, they were using that. Today also, for some of the very secret applications, defense applications, high speed, they use this. But for other commercial mainstream ICs, they do not use it, because it turns out to be very expensive. Instead, what they have done is, do not provide the whole thing as insulator. Within your technology, what you can do is, silicon can be put on an insulator, which is put on the silicon substrate. That is called SOI, silicon on insulator. Okay. So, we may have occasion to come back to that later, but today, since we are dealing with this, I just brought out this. The substrate is insulator, because that is the mechanical support, and this is single crystal. On single crystal, you can grow single crystal. That is a nice thing. That is why you are looking for materials which are of high resistivity, or if possible insulator, which are single crystal. And not only that, materials will be insulator and single crystal, you must be able to grow the layer without any defects. That means, the layer that we grow must have the same crystal orientation structure as this. Now, these are two different materials altogether. Still, silicon matches lattice with sapphire when the sapphire has a particular orientation. So, that is why they were able to manage, but still they were getting lot of defects here. So, thin layers were rather difficult, still they were able to manage, okay, and get good performance. You can get 4-inch wafer. In fact, the person who is handling it, I have seen the people handle it, they are so nervous because it is so expensive. You do not want to drop it, and you say I do not want to drop it, you will drop it. So, okay, this is the key thing about that. If you are prepared to spend that much money, and if you are not able to get as good performance as you look forward to, you can also switch out another material like gallium arsenide. And gallium arsenide, you can get a semi-insulating substrate. That is where we are telling. In gallium arsenide, the answer for that with gallium arsenide is you have a semi-insulating gallium arsenide. If you are making indium phosphide, a semi-insulating material, indium phosphide. If you are using gallium nitride, you must look for an insulating substrate, okay? Maybe silicon carbide. So, you look for high resistivity materials like that. So, since we are focusing on this right now, let us focus on this material itself. So, first you must be able to get this semi-insulating gallium arsenide material. Then you can think of putting the top layer on that, and this can be single crystal gallium arsenide, 100 oriented. On the top of that you can grow, that is what you are seeing there. On the top of that you can grow nicely that particular layer, which goes up as the time passes there. That is epitaxial layer. Epitaxy means arranged upon. You arrange the atoms on the top of a substrate, and the arrangement takes place exactly same way as the arrangement of the atoms in the substrate. Okay? Now, let us go into further details. So, first we will get into how to make this semi-insulating gallium arsenide. There are two approaches. One approach is chromium doped gallium arsenide. Other approach is in situ compounded and EL2 doped gallium arsenide. EL2 is another impurity that comes in. You are not introducing it, comes in when you grow. What is the problem here? Why should you have chromium doped gallium arsenide? Can't you grow insulating gallium arsenide undoped 10 to the power of 6 carrier concentration, which is very, very high resistivity? Can't you get that? You can never get it, because there will be impurities present. So, one of the major impurities which are present in gallium arsenide, which people were facing, was silicon. Silicon itself was coming from the crucible, okay? And silicon, you know, in gallium arsenide it is N-type dopant. So, you get, when you grow by Czochralski technique, usually when you grow from a melt prepared from a polycrystalline gallium arsenide, first you prepare a polycrystalline material, okay, and then use it as a melt, pull the crystal, that turns out to be N-type because of the silicon. And you will say undoped gallium arsenide, carrier concentration 10 to the power of 15. That sounds funny, because you say undoped, but carrier concentration is 10 to the power 15. The meaning is unintentionally, intentionally not no doping done. Whatever has happened is unintentional, but you want to bring back to the device, you want to make it insulating or high resistivity, that is of the order of 10 to the power of 9. That is about the intrinsic concentration of 10 to the power of 9 ohm centimeter will be the resistivity of really undoped gallium arsenide material, 10 to the power 9 to 10 to the power 10 in that range, when the carrier concentration is that low. How to do that? That is done by compensating those dopants which are entering unintentionally, and that compensation is done by doping with chromium. We will have it, we should discuss that, why, what happens there. Other thing that they have done recently is, do not let the silicon come in, somehow manage to grow the crystal by starting with high purity gallium and high purity arsenic, then make a compound, that is in situ compound, and then grow. That turns out to be p-type, okay, due to some contaminants like carbon, contaminants like boron coming in, that turns out to be p-type. So, you have no choice. In one way, if you already take polycrystalline gallium arsenide and melt it and grow, it turns out to be N-type from the crucible and from the contaminants. otherwise it is p type. So, if it is n type, you use chromium for compensation. If it is p type, you use that El2. Okay. That El2 is a particular name, which no expansion, it is El2 center it is called. Okay. Now, what is the thing? Okay. So, what we said is to get there, one route is so one route that you choose is chrome doped. Chrome doped or chromium doped, both are same. This introduces Y to compensate for the shallow donor. Obviously, chromium introduces an acceptor level. Okay. Now, why should we put chromium? You can put zinc. Zinc is p type impurity. While growing gallium arsenide, you know silicon comes unintentionally. You can add zinc p type. What is the problem? The problem is this: if compensation let us put it as, can compensation be done with shallow shallow acceptance? What is the meaning of shallow acceptor? Shallow means shallow level. See, for example, what we have, the problem is like this. Let me draw the conduction band and valence band like this, EC and EV. You have unintentional silicon which comes up like this. Shallow donor, which makes the carrier concentration about 10 to the power of 15 n type. If that were absent, you would have got maybe 10 to the power of 9 ohm centimeter resistivity. Now, you get very low resistivity. Suppose I put acceptors here, that is the meaning of that. Shallow acceptor I put here, 10 to the power of 15 donors can be compensated with what? Donors can be compensated with 10 to the power of 15 per centimeter cubed of force acceptors like this, shallow. Now, it is very difficult to control that 10 to the power of 15. Supposing it becomes 10% off here, you will say, okay, it is 1.1 into 10 to the power of 15, so 10 to the power of 15, ठीक है. It is not all right. Because if it is 1.1 into 10 to the power of 15, what happens? 10 to the power of 14 p type. So, you can't compensate that way. So, instead of going down to 10 to the power of 6, you are at 10 to the power of 14 p type. What was n type has become p type. Very difficult. So, control is difficult. So, what you need is introduce an impurity, which will, even if you change a little bit beyond a certain level, it is going to clamp or pin itself into intrinsic material. That is the property which gives chromium. Let us see what it is. Once we see some of these things, we can flip through those slides, because those are the things which new. Okay. This is very difficult with shallow. I have not written that, but you can just note down yourself. This is difficult to exactly compensate with shallow acceptors. Now, let us see what chromium does. Chromium in gallium arsenide is gallium arsenide, of course. Chromium introduces a level here. I am sorry, it introduces an acceptor level. You can call it as a trap level. It is an acceptor level. This is E T, just to distinguish it from the conventional shallow donors and acceptors. I call it trap level. It is actually deep level. Deep level meaning lying deep from the conduction band or valence band. It is not, please understand, deep level does not mean the impurity is lying deep. Deep level means, as far as energy band is concerned, it is actually away from the conduction band or valence band, closer to the center of the forbidden gap. So, acceptor E T, that is chromium. Gives rise to this level. I think we write that. Chromium level. Now, you have got unintentionally doped silicon. Let us see how this works out. This is E D, unintentional doped, intentionally doped with silicon, N type. Now, let us see what happens. I start with no chromium, electron concentration is 10 to the power of 15. I start adding chromium, you are adding acceptors. When this was absent, where is the Fermi level in N type material? Above the intrinsic level. This is almost equal to E I. E T in this case is almost equal to E I. In fact, you will see the next slide there, that introduces, behaves like a single acceptor trap level with E T at E C minus 0.714 electron volts, which is exactly at the mid gap of E G. The key thing is, you have introduced an acceptor at the mid gap of the forbidden gap. So, now we will see, as we go on adding chromium, concentration from 10, 100, 1000, etc., you keep on increasing, what happens? Nothing will happen until you go to about 10 to the 13 or something like that. But once you go to that level, this acceptor, what is the status of that? If the Fermi level is here, all of you know the concept of Fermi level. That is N type. As I keep on adding this, the Fermi level is below, Fermi level is above the acceptor level. So, the levels below, see, the concept of Fermi level is all the levels below that are mostly occupied, all the levels above that are mostly unoccupied. This is unoccupied means what? It has given an electron donated, so that level is unoccupied. Okay, that is the meaning of that. It can go up or go down, whatever. Okay. So, if you add here, Fermi level is here initially, this is not occupied, that is donated electrons, this is occupied. So, if there are 10 to the power of 15 electrons here due to donors, when this is 10 to the power of 12, after those 10 to the power of 15, 10 to the power of 12 will go down here to occupy that. That is where it gets the electrons from, it is occupied. So, conduction band electrons are 10 to the power 15 minus 10 to the power 12, 10 to the power 15. Keep on adding. As you keep on adding, okay, it becomes more and more p type, because you are adding a p type impurity. So, it becomes more and more p type because the electron concentration comes down. Why does it come down? It has to satisfy this. These are ionized because that is below the Fermi level. Now, so as you keep on increasing the chromium concentration, it becomes less n type, Fermi level keeps on moving towards the center. Okay. And when it reaches this point, it will reach this point, what happens? Half of them will be ionized. Okay. It begins, all of them will not be ionized. Supposing it is 10 to the power of 15, only half of them will be ionized when it comes down to that point. Okay. Now, increase it further, what happens? It has to become p type if all of them are getting ionized, but if the Fermi level comes down, if it, okay, if you add more, if it is ionized, it will become less n type and become more p type, and if it becomes more p type, Fermi level will come below that. Now, you can catch, if the Fermi level comes below that, what is the ionized state of this? It is not occupied. So, what happens is the Fermi level will actually go down. It cannot go down because then it becomes unionized. If it is not ionized, it is not becoming more p type. So, now you see, dynamically you can say keep on adding, when it reaches a certain level, the Fermi level will go, get stuck up to the middle, it will not go below that. That is the thing. So, you can see the nice thing about this particular impurity at the center of the forbidden gap is it can precisely compensate for this 10 to the power 15. Once there are 10 to the power 15 ionized impurities, if you add more, those chromium atoms will not be ionized, and if it is not ionized, it is lying there, that is all. It may affect the mobility. The maximum solid solubility of chromium in silicon is something like 1.6 into 10 to the power 17 per centimeter, not silicon, gallium arsenide is 10 to the power 17 into 1.6. So, you will not have silicon contamination beyond that. So, you can completely compensate. That is why people are able to get, they are making use of this process. When you grow from the melt, add bit of chromium. Okay. The maximum solid solubility is that. Even if there is 10 to the power 17 chromium, which is solid solubility at the temperature, how many will be ionized? They will, number ionized will be corresponding to whatever donor impurities are present, because by that time it becomes intrinsic. Once it is intrinsic, additional chromium is just lying there. Probably it gets into interstitial sites. Physically, that could be what is happening. You added much more, it goes into interstitial sites. That is what only just I could see physically, but from the point of view of this ionization, etc., very clearly see that happens. So, whenever you want to compensate, you can compensate with an acceptor impurity. Okay. In fact, about 30 years back, 35 years back, in silicon they were using this trick. Okay. If you want a very high resistivity material, 10,000 ohm centimeter resistivity silicon material, you have to sweat your guts out to get that material, because some impurity will be there which is giving it n type or p type. What they were doing was, they were adding gold, sacrifice some gold, put gold into that, and gold can compensate, it can act as an acceptor. It introduces gold in silicon, introduces a deep level at the center of the forbidden gap, that will compensate if it is n type. Okay. So, that is what people are trying to make it n type, add gold, center of the forbidden gap, whatever gold you add, all that you have done is you have wasted your gold, but beyond that point it will become intrinsic. They were selling like that, but once you use that wafer for making devices, disaster. You have bought the wafer with 10,000 ohm centimeter resistivity, but once you use that, the gold will move all around, it will get inside even into your furnace. So, you do not get good results with that. People are struggling with that. Now, today, if you want to buy 10,000 ohm centimeter resistivity silicon wafer, what you will say is uncompensated, you must say, so that the vendor does not cheat you. You should say I want uncompensated 10,000 ohm centimeter p type or n type resistivity material you can buy, then he will grow very pure crystal and give you undoped. Okay. So, this is about it. This is one way of doing the getting the semi insulating gallium arsenide by chromium doping. So, the trick is, if I have donor impurities at shallow, introduce an acceptor at the middle of the forbidden gap. Similarly, alternately, if you have a shallow acceptor impurity, if I want to compensate, introduce a donor impurity at the center of the forbidden gap. That will do the trick. You will get exactly very high resistivity of 10 to the power ohm centimeter, which you can use as substrate. Let us go further. Now, just as a matter of curiosity, I am just putting other materials to see what we are telling is true or not. If you introduce iron, okay, if you introduce iron as a compensation, it has a acceptor level at EV plus 0.39. What will happen? Supposing I have iron, okay, if I take gallium arsenide, EC and EV, I have donors, gallium arsenide, unintentionally doped. I introduce an acceptor somewhere here. This is iron. This is how much? 0.39 electron volts. So, you can see ultimately you do not have much control on that impurity that you are adding. It will be decided by its solid solubility limit at that temperature. So, it will actually come down from here, Fermi level will ultimately come and merge with this, till it comes, it will keep on increasing. So, that is why you get a doping concentration, iron doping, okay, you get 4 into 10 to the power ohm centimeter. Instead of 10 to the power 9, you get p type 10 to the power 4. That is because it lets the Fermi level come down here. It lets all of these things ionize. Okay, that is one point that I wanted to mention here. Just let us not ignore indium phosphide all the time. Let us give it a chance also here. You see, dopants in indium phosphide, yesterday itself I mentioned, they just reproduced thing on that. That is, you can make it n type, not compensation, by intentionally doping with sulfur, intentionally doping with silicon. You can make p type with zinc. Okay. Now, purest ingots of indium phosphide exhibit n type conduction with 10 to the power 15 per centimeter cube, just like what you saw in gallium arsenide. Here, if you want semi insulating indium phosphide, can't use chrome. You cannot say chrome will be introducing a level at the center of the forbidden gap for all materials. It does so for gallium arsenide. For indium phosphide, iron introduces an acceptor level at the mid gap. So, you can get semi insulating indium phosphide by doping with iron. You can rest be sure that if you do not take care with the usual crucibles which you use, okay, silica crucible if you use, that will be silicon, that will get doped from that. So, that is why comfortably they use compensation like that. Okay. Okay. Now, let us take a look at this other doping on thing for gallium arsenide. What we said is, you get n type gallium arsenide when you conventional doping, melt polycrystalline gallium arsenide, then grow, you get n type. That you can compensate with chromium acceptor level. But when you use in situ compounded, you make a compound of gallium arsenide in a melt. Do not bring a melt, bring gallium 99.9999 purity, 6/9 purity, that is called. Bring arsenic, again 6/9 purity, 6/9 means there are 6 nines, 99.9999. You bring the mix up. From there you start growing. Okay. It looks very easy. Why did you not think of it before? Okay. You have thought about that, but you are not able to do it. You bring gallium and arsenic, keep them together like this, heat them, because after all First you must make a gallium arsenide melt, from there you must grow the crystal. When you heat them, you go to the melting point of gallium arsenide, you heat. The vapor pressure of arsenic is 60 atmospheres at 1238 degrees centigrade. Okay? That is very high. So, what will happen as you start heating? What is the vapor pressure meaning? Let us just take a look at that. What is the meaning of vapor pressure? When I say I put arsenic here and I heat it, the vapor pressure is so much means, in what the implication is, if I put in a vacuum chamber, I keep arsenic and heat, it will start losing arsenic. Arsenic will start evaporating till the pressure of arsenic vapor is sufficient to prevent the loss of arsenic. See, for example, if I say 1 atmosphere is the vapor pressure of arsenic at 500 degrees centigrade, that means if I heat it to 500 degrees centigrade in vacuum, the solid arsenic will start evaporating, collecting in the vacuum till the pressure is 1 atmosphere. You evacuate and start heating till it is 1 atmosphere, then it will stop evaporation. So, if you maintain a over pressure of 1 atmosphere of arsenic, you will not lose it. Now, here you have a problem where you have to go to the melting point of gallium arsenide, 60 atmospheres arsenic over pressure, God forbid you can't do it, okay, unless you have that arsenic pressure built in or some other gas pressure you must bring in. That means you must have pullers, crystal pullers, which can bear the pressure of 60 atmospheres. Can you imagine what will be 60 atmosphere? Just imagine 10 atmosphere, even that is terrifying. Why is it terrifying? It is like a bomb. It is really like a bomb with so much pressure. 60 atmosphere is so much. So, if you have a chamber, it must withstand that much pressure. Those were the difficulties people had, but today, as we go on, we will see people have overcome some of those difficulties and they are able to grow that, but when you do that, you get that material p type. Fortunately, there is a deep impurity which comes up, okay. That deep impurity is EL2, that EL2 is the name given, it is actually a defect. When you grow the gallium arsenide with slight over pressure of arsenic, you increase the pressure of arsenic somewhere so that you do not lose it. Okay. So, the over pressure of arsenic, when you grow, you get arsenic sitting on the gallium site, and arsenic sitting on the gallium site turns out to be N type, it is a donor. So, a defect of arsenic anti-site, instead of sitting in its site in the 5th group lattice site, it is occupying the gallium site, that is called anti-site defect, that is a EL2. So, that defect gives a deep donor at the center of the forbidden gap, which can compensate all the p type impurities. Okay, we will see more about that. So, EL2 is run by in situ compounded gallium arsenide, that we will see now how to do that. You first compound it, and then when you do that, you must have a cap being put to prevent the loss of arsenic. Okay? You put a protection cap to prevent the loss of arsenic. So, I just do not go into the chromium doped now, because chromium doped is, once you have the crystal from a polycrystalline material, you add to the metal chromium, that is rather simple, you do not have to worry about other things. Here, this EL2 doped semi-insulating gallium arsenide is very popular today, because if you can get without intentionally adding materials like chromium, then that is a technology. Why? If you have a substrate which is chromium doped, if I have chromium doped gallium arsenide which is semi insulating, on that you grow an active layer. You grow an active layer. You do it at higher temperature afterwards. This has chromium. This one you want to grow at a doping of 10 to the power of 14, 15, 16, that is active layer, N type. Now, when you grow that at higher temperature and do any processing, that chromium gets inside into that layer. all these deep impurities which are added deliberately, they can diffuse. It gets into this. Once it gets into this, the properties of the layer which are growing changes. That was one of the major problems people had when they were making the gallium arsenide devices, 1980s. But after that, the problem has been sorted out without adding chromium. So, in this case, what they were doing was, don't put the active layer right here. What do? Put a buffer. So, solution is put a buffer layer. Okay. Buffer layer. On the top of that, you grow your active layer. That is what they were doing. So, in case when you see in the publications, if you see a buffer layer put, that is mainly because it is a chromium doped. When you use semi insulating substrate where you have not added deliberate impurities like chromium, you do not need buffer layers. Straight you can grow other layers. Let us go back into this now. Okay. The approach, now you can just quickly see, we understand what is needed. We need gallium arsenide made with pure mixing of pure gallium and arsenic. So, place high purity gallium, that is the 6-9 purity, and high purity arsenic in a heated graphite crucible coated with pyrolytic boron nitride. In fact, that takes care of any of those silicon contamination etc. coming up. Okay. Some of the contaminants from the graphite crucible also is prevented by using some coating of boron nitride. Okay. So, that is what is done there. Then you now right now you put it in a crucible there. I have to show you a picture so that it is visible to you. See what exactly happens. This is the crucible, pyrolytic boron nitride coated crucible, arsenic, gallium. You put them together now. That you put your gallium above that. How is it gallium is above that? Arsenic is solid, gallium is liquid, even at 29.5 degrees centigrade. That is why put it on the top of it. Okay. On the top of that, you put boric oxide, B2O3, and B2O3 actually is, it is a cap that you provide. It will melt by about 450 degrees centigrade. So, what you have to do is, you put this disc of B2O3, which has undergone all baking etc., put it on the top of it, now heat it. Let us go back to that. So, place B2O3 disc on the above gallium and arsenic stoichiometric mixture, 50% by weight of gallium and arsenic, 50-50, okay. That you put, and then put this cap, and here you see it as a disc actually, it is not yet melted. So, the system, its whole thing is the system, enclosed system. You have to pressurize the system to about 3 atmospheres. So, that is where the catch is. You must have crystal growing systems which can go to those high pressures, 3 atmospheres of nitrogen. You do not have to have arsenic, you have the nitrogen pressure to prevent the loss of arsenic as you heat up. So, heat to about 450 degree centigrade. At 450, what happens is your B2O3 melts, and once you melt the B2O3, okay, and it floats over gallium and arsenic. You have chosen B2O3 because it should not react with that gallium arsenide. One, it should be lighter than this gallium arsenide, so it float. It is not at the bottom, it should remain on the top. So, well thought out cap, not the ordinary cap, well thought out cap, which melts and floats on gallium arsenide. That is okay, to prevent any loss of arsenic when you pressurize from the top. So, that is, let me come back to this. Okay. So, once you do that, once it melts, what you do is, this is the time 450 degree centigrade, arsenic and gallium have not reacted. All that you have done is you have melted the, you have molten B2O3, okay, which is protecting with the 3 atmosphere pressure. Now, you want to jack up the pressure to higher level where gallium and arsenic will react. Okay. But you can't do that without increasing the pressure. So, raise the pressure to 60 atmospheres. That chamber can withstand. That was the catch earlier. Now, you have those crystal pullers which can withstand those temperatures, okay, and then heat the crucible to 700 degrees centigrade. Reaction of gallium and arsenic occurs to form gallium arsenide. Once that is, it has melted, you have the compound formed gallium and arsenic at lower temperature. Now, you do not need the 60 atmosphere, because this is a very important thing that you should note. Vapor pressure of arsenic over arsenic, if you take arsenic itself, if you go to 1200 degrees centigrade, that is 60 atmosphere. That is why you are using this 60 atmosphere there. But once you have gallium arsenide, if you heat the gallium arsenide to the melting point of gallium arsenide, the vapor pressure of arsenic on gallium arsenide is 1 atmosphere. That is the nice thing. Okay. The vapor pressure of arsenic over arsenic itself is 60 atmospheres at that temperature, but vapor pressure of arsenic over gallium arsenide is very low. So, that is why once the compound is formed, reduce the pressure to 2 atmospheres, that is sufficient to prevent the loss of arsenic with the cap of B2O3, increase the crucible temperature to 1238, that is the melting point, 1234 plus 4, melting point of our gallium arsenide. Then insert the seed crystal with 100 orientation, pull, rotate and pull. That is the Czochralski technique, and this is what you see here. Gallium arsenide melt and the seed crystal dipped into that thing and then pulled gradually, rotated. Today you can grow 3-inch to 4-inch rods of gallium arsenide. That means you can have wafers of 3-inch, 4-inch diameter comfortably with which are semi insulating. Okay. And you can see there all through this B2O3 is the protector, that is lighter than this gallium arsenide, density lower, therefore, it is a cap all through, and you may get a coating of that on this wafer crystal as you pull it. All right. So, this is the called the LEC technique, liquid encapsulated Czochralski. Normally for silicon you use the same technique, that is Czochralski, where you do not put all these layers, protective layers. You do not have to go to high pressures, you can just grow it very easily, because vapor pressure of silicon at the melting point is very, very small. You do not have to worry loss of silicon. Even if you lose silicon, what happens? You lose that is all. You still have silicon. If you have gallium arsenide, if you lose arsenic, what happens? You have gallium arsenide which is rich in gallium, okay? And if you lose too much, you will be left with only gallium, which is liquid. Okay. So, now this is just for fun I put it, so that because this is a puller, crystal puller, what we are seeing like that and all, that portion that is here, that is the crucible, this is the melt, you can see the thing clearly, and this is the crystal which is being pulled, and you can see that is rotated and pulled, rotation, pull speed, everything governs your diameter. Okay. So, this is where the crystal grower, he views how the hell it is growing, is it going all right, are you having any pinning, twisting, etc. taking place. So, this all should be done in a very vibration free table, because any slightest tap there will give twins, defects in the crystal to twist. Okay, so, that is actually the growing of the melt from the melt gallium arsenide, and the system this should withstand that high pressure. And you can see this is the heater, it can be resistive heating or RF heating, either way you can use it. Now, EL2 doping of gallium arsenide comes into picture. I have already mentioned to you that gallium arsenide, okay, gallium arsenide is p type when you grow like this, if that EL2 are not present. Okay. So, it is about 10 to the power 14 to 10 to the power 15 per centimeter cube. This is due to contamination from that boron from the B2O3, that seems to make it p type 1, and also it is the carbon incorporation from the crucible little bit to some extent. Okay. These two things make it p type gallium arsenide, but that shallow dopant can be compensated by the native defect, which is due to the arsenic occupying the gallium, which I have said already. Okay. This is put here in black and white or in color. Gallium site, arsenic occupying gallium site. It is sometimes written like this, wherever arsenic gallium is supposed to be there, it has pushed the gallium and arsenic is sitting there. That is the idea of that. So, that is the symbol that is used, anti-site, and gives a donor level at EC minus ET equal to 0.75. That is almost close to center of the permitting gap. So, that is where you have got LEC gallium arsenide. It does not have the donor, it has the acceptor, and then you get EL2 center, which is anti-defect. Okay. So, this is the result of the defect, which you normally may not like, but you like it here. You do not have to worry about this particular defect moving into the next layer. Okay. It is not like the impurity which will run. So, that does not move into that when you, unless you go to the liquid melting point of the gallium arsenide. EL2 is due to arsenic overpressure. Growth from the melt with arsenic concentration greater than 0.475 gives excess arsenic in the solid. Okay. I just put that diagram here. The statement you can just note, even if you do not have to grow from the stoichiometric melt, even if it is slightly on the left hand side, that is less arsenic, not 0.5, slightly less, 0.475, then also when you freeze it, pull it, it has excess arsenic, and that sits in the gallium site. Okay. So, people have found that you can get 10 to the power 9 ohm centimeter if you have the stoichiometry and above or slightly below that. I will just draw the diagram here now. What I draw is what I drew yesterday again, because that is relevant here. Just remove all these things here. So, what you remember, gallium arsenic, okay, and what we drew yesterday was 29.5 phase diagram, and then here 0.5, which actually is the solid line, which actually represents a region like that. When you see the whole thing, you get like this, then you have got like that. Above that line is liquid, and here you have got liquid plus solid, liquid plus solid. If I expand this again, what I showed you yesterday, because that is relevant here, so we wonder why that is happening. I have 0.5 arsenic, 0.5 gallium, and this is gallium, this is arsenic, 100%. Okay. Now, if I draw a line like this, that one, okay, you expand this line alone, I import only this portion, then what you get yesterday what we saw was something like this. Something like this really. I am not able to draw it very neatly. This is expanded view of this, and on the top of that you have got, that is the liquid. So, now you can see when I freeze from here or here, the solid that freezes, where does it go? it goes into this. If I freeze from here, which is less than 0.5, 0.475, when I freeze, okay, the freezing solid is, this is liquid plus solid, this is liquid plus solid. So, solid will be there. The freezing solid is, has that composition. That is the meaning of the phase diagram. So, if I have the composition corresponding to this here, that is arsenic rich, slightly arsenic rich. So, you have excess arsenic and also gallium vacancies. Those excess arsenic atoms go and sit in the gallium site, which is anti site and which actually becomes beneficial for you to compensate for those carbon or boron impurities. So, if I go on to this side, if I go on to that side, till all the time you will get this one, but if I go on to this side, you may not have these anti-site defects, because if I come down from here, it may come here, just about stoichiometric. Okay, the melt. The melt is actually not non-stoichiometric, but composite that you get is arsenic rich. That is what you are looking for. Okay. So, that is why you get high resistivity materials when it is more than 0.75, 0.475 arsenic. So, to sum up, what you can get now is semi-insulating gallium arsenide material you can get with this technique with the help of the EL2 center. You do not have to do chrome doping. These are the material which is used these days for making integrated circuits as the starting material. We will continue on this tomorrow, because next we will see the top layer on this epitaxy layer. That part we will discuss next. Okay.